Hello everyone, welcome back to the session 6, week 6, tutorial 6 for this course, Nuclear Astrophysics. Let us wait for some time for the students. I hope they will be joining by some 5 few minutes. So yes, let us wait for that. But yes, these are the week 6 topics that that was covered in the lectures. That is formation of 12C, survival of 12C, carbon, neon, oxygen, and silicon burning, nucleosynthesis beyond iron, SRP processes, and these were the main things, main topics that were covered there and in very elaborative manner. So I will not discuss about those things again and again. Rather, we will solve many problems today. We will do the modeling of a star. There will be revision. There will be some MCQs, and this is the plan for today's thing. So main thing is that now your Hmm. Uh, now your end term examination is coming close, so you need to prepare for miscellaneous problems and for whole topics, all the topics that have already been covered in this course. And by now you have already the idea of main things what you are going to learn and what you have learned. And so yes, so now it is a time to recall all those things. Let us wait for a few minutes while the people are joining. Then I will start.
Good evening, ma'am.
Good evening.
Ma'am, when will we get our admit?
Okay, it is not out yet, but you will get within the last week, I think, before 1.5 week and like that.
Okay.
Okay, before the people are joining, let me talk with you guys whoever has joined and what is the status, how you are going through this course, and how are you feeling.
It's quite good, ma'am. We are listening to your lectures. It will be very easy for us. It is very easy for us than seeing the videos which is also uploaded by the NPTEL portal. It's quite difficult to understand, ma'am. I saw one time in that full video I saw at once. In my maiden view, I didn't understand clearly, ma'am. Maybe I will, if I see the next time, means I will, there will be a possibility to understand better. So, my status now.
Okay.
You told me right in last session binding energy of the nuclear. I asked right now nuclear fission or nuclear fusion better. So
Mm-hmm.
I go through some websites. It tells a fusion reaction require more energy
Mm-hmm.
due to the fusion of the two nucleus. It required more energy to fuse.
Yes.
So that's why I find out. But you told to find out the binding energy of.
Hmm.
I am not. I don't know about it, ma'am. Can you please teach me that?
Okay, so you are finding it problematic to calculate the binding energy?
Yes, ma'am. Yes, ma'am.
Okay, so okay, at last we will discuss about those things. Okay.
Okay, ma'am. Okay.
Okay. And anything else, please feel free to tell me that what you are feeling like. You have any doubts, you have any question, any other topic you want to be covered. Anyone? Do anyone have any problem like something you need any revision, something which you did not understand or which you want to be included in this course, or you want to be discussed with you guys, or what are the things that you want to, if you want that if it is done here then it will be more helpful for you. Is there anything like this? Then you can tell me.
Okay, ma'am. I have one query.
Mhm.
When will the video is a bit because the videos which are uploaded by the NPTEL portal, it is quite 2019 videos are repetitively uploaded, ma'am, in the consecutive years. So when will they upload, updated and can I understand, ma'am?
No, sorry, I did not get your question. That what are you talking
Ma'am,
about?
in NPTEL portal,
Hmm.
they uploaded the professor video right now. That video is a too old version, I guess, ma'am. It was uploaded in 2000, since 2019. They uploaded the same video
Yes,
next
yes, yes,
consecutive years, ma'am.
yes.
So if they updated the video means it will be useful for a current trend
Yes.
video.
Yeah,
I feel that, ma'am.
that's absolutely true. But all the courses which are running, most of them are like already recorded and like which are the lectures and the discussion sections are only the things which are the current things.
Okay, ma'am.
Hmm.
But many of them are not aware of this live sessions, ma'am.
Okay, they are not
That's
aware.
the reason. I see, ma'am.
That's a problem. Actually, yes, uh, that's a problem. But I don't know. That is not conducted by us. That is responsibility of somebody else's, like to spread these things.
Okay, okay, thank you, ma'am.
Okay, but yes, your points are very valid. They are true.
Okay,
And
okay.
Godhuli and Kavya, do you have anything to say?
Ma'am, I have a problem in the resonant reaction thing.
Mm-hmm.
I cannot understand that very well.
Okay.
The resonant reactions and the neutron induced non-resonant reactions.
Mm-hmm.
Uh, I could
So,
not understand them like the formulas I could not do in the assignment very well.
did you go through the lectures where I solved the numerical problems in details?
Yes, ma'am.
But still you are
But I'm
finding
facing
problem.
it problem in like applying the formulas while solving the problems.
Okay, that means when I was solving also, then at that moment also you did not get it properly.
Uh, Yes, ma'am. In the specific problems which you did,
Mm-hmm.
I could understand them. But while solving some new problems, but I couldn't understand that which formula to apply. Like in the lectures, sir has said many
Formulas are
formulas
there.
regarding
Hmm.
the stellar reaction rate. Sir has told about three formulas. So which one to apply? Cannot understand that one.
First of
Like
all, you need to find out the condition which will be told, which will be there in the question. And second thing, you need to get the idea that what are the parameters that is already given to you and you can calculate, such that you can solve the other part of the problem and get to the real parameter that is actually given to you to calculate. But so you can do if you just like, there are two fundas, like first of all you need to understand the conditions that which are given as a condition. According to that condition, which formula will be used. And second thing is that suppose in a formula sigma v mean that you are calculating, there are various variables and parameters inside that formula. Now there are various type of formula or various formula for this calculating this sigma v itself. Like there are three or four formulas as you are saying. So there
Yes, ma'am.
in case of first find the conditions that which are you gonna to apply because of this problem, for the particular problem. And if you then also don't understand, or if you finding that I am not getting that what formula will I use, then check that which are the parameters that is already given to you, and according to that what you can calculate. And when you will get that parameters, then by putting those, which formula will be the main thing with which by using which you will be able to calculate that sigma v thing, or the right side parameter, anything whatever is told to you to calculate. So these are the main things. But even after that also you are finding problems to solve these questions. Then maybe did you try to solve those problems to solve again by yourself after doing here?
Yes, ma'am. I tried again on my own. Then only I couldn't do it and have to see your sort thing again.
Okay,
That's
that
the
means that means there
problem.
is a problem of understanding of the the process of the process of the solving of these problems. So that means you have to understand. Maybe we can do one thing that first you need to you take a paper and write the question yourself and find out the points, which are the main points that is given to you. Then you of course you can see the videos multiple times, or the materials that is already provided to you in the Google Drive, that what are the things there. You see them, then practice them by seeing them, then do by yourself again. But while you are doing that process, every time and each time you need to understand that why I am doing this, why I am using this formula, and how why I am not using the other formula. So by this way, if you can analyze yourself, then one practice is one of the main key to solve all these questions. So
Yes.
after that you will be, I hope it will be better, there will be some betterment in the or the improvement in the solving of these questions.
Okay. Ma'am, we have to remember all the formulas that sir gave for the final exam.
Yes, mostly you need to remember, because the formulas will not be provided to you. Which are the formula that I boxed it up? Those
Yes,
things
yes.
are very important. Maybe I can make a
Oh,
formula sheet for you if you want, then, and provide if you find it, it will help to you.
okay.
Okay,
Ma'am,
ma'am.
especially in the week 8, lecture number 39, there are means a huge number of formulas. So, ma'am, I don't know how to remember all of them. Like there are 20 or 24 formula
No,
in only one lecture.
you don't need to remember in such a way like to memorize it. Like what I found for week 8, I don't know that what formulas are you talking about, because yes,
And that
I
center of mass and mass frame and laboratory frame transformation things.
okay. But I don't think that you need to remember all those formulas, because every formula is not necessary to remember, or not necessary to remember that you will be getting a question from that particular formula or not. But the main thing is that suppose I have some problem with me which is about to solve a projectile motion. Then if you are going for any competitive exam, then it will be very helpful if you remember all the formulas of time of
Yes,
flight,
ma'am.
the height, and all those things.
Yes,
but
yes.
but when I do it by myself, I never remember
It's
those
huge
formulas.
time. Like deriving requires huge time, and we won't be
It will,
getting that time
you
to solve.
can't derive all the things in this case for these nuclear astrophysics course, because it will take a huge amount of time. But
Yes, ma'am.
there is some key things like, if you consider the cross section, or the cross section and the sigma v mean, then what is that? That is a cross section, that is area squared into some v, that is the
Hmm,
velocity,
hmm,
then the mean
hmm.
of that. Then you can analyze that if it is a MCQ type question, if all the units are same, dimensions are same, the order of magnitude are same or not, then which order of magnitude can be possible for this type of question. Like, these are some intuition, and not only the intuition, you can't go through the all the details of the formulas, but rather the proportionality, like it is just varying with the t to the power 4 or something like that. So these are the main key things that you need to remember, because many of the problems here in nuclear astrophysics will be solved just by using the ratio, and just by
Yes,
using you don't need to remember the proportionality constant all the time, because there are many constant part also. You have to
yes, yes.
you have to get the feel that, if I have some parameter, then with which power, or with which thing, or how it is varying and why it is happening. So that is the main thing that will help you to, yes, for first time doing any course, that is hectic, that is not easy to remember. It happened with me also. But over the time, if you are with these things, then it will be, you will grasp all these things easily. But yes, whatever problems you are facing, that are very natural, that I have already felt, and the people who used to take these courses, they also felt. So the main thing is practice, and try to understand as much as possible, at this moment at least.
Okay, ma'am. Thank you.
Okay, so and, let us start today's discussion. And I will not show any slide mostly today, because today I have some internet bandwidth issue, because of our internet of institute system is already is down today for some working is going on. I don't know what is going on. What was there? There was, in this week 6 content, there was formation of 12C, survival of 12C, that is carbon, then carbon, neon, oxygen, and silicon burning, then nucleosynthesis beyond iron, and SRP processes, all those things. And most of them were very it discussed in very elaborative manner by professor. So and one thing is noticeable for here, that in these for these weak questions, you got mostly like very informative question. And I expect in your in your end term examination also, the questions which you get from this new burning part, like week 6 course content, those will be mostly for those will be mostly from information based questions, not like very rigorous numerical problems, which you already have solved some. There will be nothing like that, but there will be informative questions. And I found personally that informative questions are more dangerous sometimes, because you need to remember the things particularly. And yes, there were lots of questions this time with the spin parity. I think two or three questions are there for the spin parity, and I hope everyone were able to solve those spin parity type of question this time in week 6 assignments. If anybody find any problem, or it was very easy for you to solve these questions?
No issues, ma'am. It's easy, ma'am.
Okay, that's very nice.
Yes, ma'am. Week six assignment was easy, but I was solving the week seven questions. It is a bit difficult. Like I couldn't get it from the lecture.
Okay, so week 7, next day I will discuss. I will try. I will try to find out that what may be the problems that you can find out, and I will discuss all those things. But as far as our rules, I need to discuss week 6 for today. So I can't jump actually. So for that reason, I will not go through week 7 content today, because of the things rules that I need to follow. But yes, I will definitely do that in next upcoming week. we what plan I have today is that I have already started the modeling of a star thing, so I will complete that, and we will do a lots of revision today, and I'll go through the week 6 questions once. I'll ask that what you guys have done and how you guys have done, such that I can understand that you guys are very pretty well with all these things, because I found this very easy now, and you should also find these things very easy now, because these are these I have discussed in previous classes also. So yes, but revision is necessary, because the end term examination is already coming very soon, and I hope many of you are going to write that examination, as well as this is very important that when you are taking a course, that you don't forget what you have already learned. So, and I found that astronomical distance, luminosity, those type of questions were not there in the assignments very properly. So today I will discuss some of the problems that I have made for you, such that you can get you can remember all those things, revisit all those things, and try to solve by yourself. And also I'll be able to see that if you guys are can capture it, how well you guys can capture it, or all those things. So let us start our discussion today. First I will start with modeling of a star, because this is a long derivation that I need to do today, and there were this was in hold for a longer time, and I have started this in the previous class itself, but yes, I could not complete it. Today I'll definitely complete it, and then we'll solve questions, then we'll discuss week 6 assignment questions also. And I think do anyone have any problem in week 6 content? I don't think so, but still let me ask you guys that do you have any problem in the week 6 content? This was pretty like I found week 6 content was pretty easy. Okay, if not, then let me start with the modeling of a star. So what as about the assumptions, I have already discussed these things, so I'll just write the assumptions whatever we have taken. We took the assumption. First assumption was isolation, that a star is totally isolated from the others and they don't interact with each other. In such situation, we are considering an ideal situation for the star, and we are modeling for such a star. So this is isolation was the first assumption. Second assumption was composition. Third assumption was spherical symmetry. Fourth assumption was the star is in local thermodynamical equilibrium. Then the fifth assumption was over shorter time scale, LTR and LTR of stars seem to vary. Like they are not stable. Obviously, there will be some variation with time. Okay. Okay, now let us start that what are the variables or quantities that are what are the quantities that are going to vary when we are studying a modeling starting to model a star, or dynamic of a star, like what how it will vary with the time. So in that case, we found out that the quantities which are the variables, those were first of all density, Rho is a function of RT. R means also the mass, so it is a function of mass and T. Then the temperature, T is a function of R and T, and that means it is a function of M and T. That means I can write in terms of R or in terms of M. That does not matter. Maybe both will be required for these things. So I am writing in both manner. And then the composition, that will also vary. That is what the composition part is. A composition, density, temperature, all of the three will vary with the time. And why it is varying, the main cause of why all these are happening, that is the part of the nuclear astrophysics course that you have studied for these long 8 weeks. That why is this happening, what main cause is nucleosynthesis, that now we are already aware about S process, R process, P process, all those things. So this is a perfect time to understand that how these will vary, and what is the modeling, what is the modeling, how can we model a star, and dynamic of a star, how it is, what it will be. Because stellar evolution and stellar astronomy is one of the such thing where we use the nuclear astrophysics mostly. So yes, this is the composition. So these are also depend, that is equal, if we call that this variable is suppose x, then it is a very function of R and T, and we can write it as this, where xi is equal to mi by m. Why? Because there can be many kind of composition, like there is like hydrogen, helium, many things are there. For that I is there, like there is some amount of hydrogen, helium, but now here we are considering all the things together like a composition. So the thing is, everything is telling us that mass will vary. That means dm, and that we can write as 4 pi r square rho r dr. I hope this can be understandable for everyone, that how we can write dm is equal to 4 pi r square rho r dr. Everyone can understand this? Anybody?
Yes, ma'am.
Okay. So the so now the some notation that I will write here, like for when I'll do any kind of special derivative, that means dx type of derivative, then I will write d. And when I will do any kind of time derivative, then I will write it as delta. These are the convention that we are going to use here. Otherwise we will be we'll end up with some messing situation. So let me clear with that. So first thing is that whenever we do any modeling, the things we need to remember is that there will be always the conservation of energy. So we'll deal with conservation of energy. Two is conservation of momentum. These are very fundamental things that always going to happen, and this is true. These are the principle of or law of nature, that it will always be true for any system. So studying any system means you need to follow these two conditions. Now the third thing is hydrostatic equilibrium. Okay, so these things, for these three things you will get three stellar equation, which we call first stellar equation, second stellar equation, third stellar equation. So first will come from conservation of energy. So so conservation of energy, for that we have already defined that what are the parameters or the variables that are going to vary. But let me go through some details more. That is, here it is happening conservation of energy because of heat which is absorbed, that is equivalent to change in internal energy plus work done. So this is a conservation of energy, that heat which is absorbed, like there are composition, there are some materials like fusion is happening, like right before this discussion, someone was talking about that, I that previously we talked about the fusion and fission thing, and to check all those things, that what is the thing that is happening, there is happening fusion, as he also mentioned. So according to that, we already know that there is some amount of energy, and temperature is also a fact of energy, nothing more than that. So some amount of energy that is needed to be inputted in the particular nuclear reaction, such that the fusion can happen. So for that reason, there needs some heat absorbed, and whatever the absorption of heat is happening, that should be balanced with something else, other than the system will not conserve the energy. And for that absorption is balancing with the change in internal energy and work done. So if this is the conservation of energy for a ideal case which we can consider, and for the ideal case, and for the simplest case in case of star. If we consider that, then there are coming few variables or parameters here again. One is that we have already I have already mentioned about internal energy. So if there is internal energy, that means there is change in the energy, something is happening there. There is something like compression and rarefaction kind of thing is happening here, like heat is absorbing, something is pulling back, something is pushing. So there will be some difference in pressure also. So from that perspective, there we will introduce some other variables, and one of them is obviously pressure, because there will be some gradient in pressure inside the star, which is balancing, which is one kind of conservation of energy itself. All right. So the other parameters which we'll be using, those are all the thermodynamical parameter, mostly. So they are, first of all, the internal energy per unit mass. That is U. Then pressure. Pressure is equal to P as a function of MT. I have already told the main, these are the parameters, and main variables are these, M and T. M and T means always R and T. So next is the energy going outward per time, per unit time, that is equal to L as a function of M. Why? Because if this is a star, and with the time it is expanding. If it is if star is in primordial form, and if it is going to its red giant and giant form, then it is what it is. What is actually happening? It is actually happening that R is increasing. That means the dm, there is some dm, that some mass is adding, and which is actually nothing but the rho dv, as we all know that from the relation of volume and the mass. Then the main dynamics of the star is nothing but the evolving in its radius as a function of time, that how it is going to vary with the time, and how much amount of mass it is adding, and how in that manner it is conserving the energy. So this is the thing that we are going to implement to deduce our first stellar equation. So this was the m first, then some dm is adding, and now it is becoming m plus dm, and this is nothing but dm is nothing but rho dv. So something is going, and this whatever energy we are getting as a luminosity, like what reaches to us is flux, but what is the original thing that it is emitting before getting any absorption, but before there is any absorption in the atmosphere, that is called the luminosity, that I have already discussed with you, that what is the difference between luminosity and the flux density. We will solve some problems about luminosity today. but I was in the very first class, I think very first discussion, or second discussion, maybe I forgot, maybe week 2 discussion, I have discussed about the luminosity, flux density, what are the difference between them, and how we can calculate those things. So now all these things will be applied and will be needed for this discussion of stellar structure. So and last but not the least, nuclear energy released per mass, per unit mass. Sorry. Let us denote it with qm, q as a function of m. That means first is radius, suppose r, it is r equal to 0, then it is suppose r equal to r, and now it is r plus dr, and it is continuous, it will increase. Then m, another thing that will also have the same thing, m at this point, m plus dm at this point. Now it's L, luminosity, that is the energy going outward per unit time. So that will be like L here and L plus dl here. And next thing is Q, that is the nuclear energy released per unit mass. It is Q here and Q plus dq here. So another thing is that now what we are going to use, we are going to use the laws of thermodynamics. First law of thermodynamics is nothing but all we know that these are the conservation of energies and all those things. So we will use that as we are talking about conservation of energy here. So we will use the first law of thermodynamics directly, and these are all thermodynamical variables that I have already mentioned to you. So let me write the first law of thermodynamics. You can see one thing, that when you will study these advanced courses like nuclear astrophysics and mostly astrophysics and all those things, all those stuff. You require many things, like you will use mechanics, you will randomly use, you will use statistics randomly, you will use thermodynamics also. Like you need to have a intuition, all those things, then it will be very easier. Or you can maybe think in this way also, that if you do this kind of study, then you will be able to get in touch with all those stuffs which are basic physics stuff. And by using all those things, we are developing such kind of modeling. And by this way, by doing the modeling of a study, you will be able to understand that how we actually do any kind of modeling. Not only modeling of a star, now in this time, like nowadays in research, mostly for those who are the computational physicists, computational work whoever do, they do this kind of modeling, they develop modeling, they try to simulate it, that how it is happening. Like sometime ago, when I was doing one project like a hydrostatic equilibrium thing, then we are trying to model it, like how Rayleigh Taylor instability, like other instability, like I'm not getting remembering not right now, but how all those instability will behave, will actually happen. For that, our tool is computation, and what we need is the basic physics. Here we, and by doing this modeling of a star, you'll get an idea that how to do any modeling of a physical system. Okay, so this is just I mentioned because whoever is going to research in any domain, like modeling is one of the very main thing that is that you need to, not for this star thing, like for anything, modeling is very important, and modeling of any system is one of the very important thing that you need to do nowadays in a research. Okay, so this is the first. Now we'll use the first law of thermodynamics. And we know what is that, that is a delta q equal to delta u plus p delta dv. And I have already mentioned, when I will use small d, then it is special derivative, and when I will use delta, that what I'm using right now, then it is time derivative. So it is time derivative. So delta dv, sorry. So this is the first law of thermodynamics, which I can write at 1. Then delta U coming into the its role come into the play, that delta U was the change in internal energy with the time, which is nothing but UdM. What is
Ma'am,
it? Yes.
ma'am, in the first law of thermodynamics, it will be P dV only or P delta dV
Sorry. P
formula.
delta
The first
dV.
law of thermodynamics,
Hmm.
that will be P dV or P delta of dV.
Okay. Normally, what we write? Normally, we write Q equal to U plus PdV, right? PV,
Yes, ma'am.
or delta Q equal to du plus P
P
delta
dV.
V, right? PdV.
Yes, yes, yes,
So
ma'am.
the thing is that here we cannot write this, because there we don't consider the variation of time and mass at the same time. We consider a system at a particular time when we do the thermodynamical thing. But here this is varying with the mass, that is, which is specially happening, that for that reason it is dv, but as well as it is varying over the time. For that reason we
Okay,
need to consider that using that delta dv.
okay, ma'am. Okay, ma'am.
All right. All right. So that is the thing. It is good that you noticed that and tell me that. I forgot to tell. Yes, please feel free to ask question anytime, that you whatever you find, and that I'll be very helpful. That is very, that I'll also like. So okay. So delta of udm. Now udm is the internal energy, which is u, small u, that I have already written. That is the internal energy per unit mass, and that is u into dm, that is varying with the spatially with the mass, and now it is the variation with the time, which is delta u, the total which is actually the change in the internal energy over the time. So these are the thermodynamical laws which are using, which, or thermodynamical parameters which we are using, but with slight variation, and that is how we are developing the modeling. Obviously that will we will directly not use that, because if we directly use that, then it is just a simple thermodynamical system. But we are not considering that. We need to consider the nitty gritty things, or the simplest possible way to think that how it is, how we can model a star. So for that, for two things that we need to remember, it has a spatial variation, and spatial variation is happening over the time. So we need to consider two kind of derivatives: spatial derivative, which is denoted as small d, and delta, that is time derivative, which is denoted as delta. And this is the first law of thermodynamics in this case for this system, and this is the variation of internal energy over the time, that is delta of udm. And u is small u is the energy, is the internal energy per unit mass. So now you can write delta dv also. Delta dv is delta of dm by rho. I have already written that rho is equal to dv dm. So dv is equal to dm by rho. That is where that is what I am writing here. So this is nothing but delta 1 by rho, the density that will vary, and delta dm will come out of it. So that is what that is the delta dv. Now what I need to calculate is delta q, that is heat generated plus heat transferred. So that is equal to q dm delta t plus lm minus lm plus dm into delta t. So it is nothing but like this kind of things, q dm, which is q. What is q? Q is what is q? Q is nothing but the, where it is, q is nothing but the nuclear energy released per mass. Yeah, here I have written nuclear energy released per unit mass, that is the qm, and that is adding with the dm thing, like whatever happening for this dm increase in delta t time. For that reason we are doing q dm into delta t, variation of dm in delta t time of the nuclear energy that is released, that is the cause of the heat generation and that is written as q delta dm into delta t. And now and the second half is like heat transfer. And what is the heat transfer? That is, when it was at this position, it has mass m only, then it has some energy, it has some luminosity what it was giving to us, that is lm. Now now it is emitting, now it has a mass which is expanded to m plus dm, and time has also varied from some delta t time has also elapsed in between that time. Then what I have, like, we are getting the luminosity now from l m plus dm. So the change in the luminosity, what has happened, that has happened is l m minus l m dm, and that is with the variation of time, like in delta t time. So we are considering, sorry, we are considering l m minus l m plus delta m into delta t. So that is what is heat transfer, because that is the first it was giving luminosity lm, now it is giving l m plus dm, that is the heat transfer which we are considering here. So that is the total, now delta q is the total energy, to, what is absorbed plus what is transferred. So we now know all the three parameters that we need to know to use this first law of thermodynamics. First thing is delta q, second thing is delta u, third thing is delta dv. So from equation 1, so from 1 and whatever we have written now, from that we can write the first law of thermodynamics in terms of these variables. So what it will be? It will be dm q dm delta t plus sorry, not plus q, that is a q, sorry, this is the delta u. Let me write all those things first. First is delta q, that is a q dm delta t plus lm minus lm plus dm dt delta t equal to du, that is equal to delta u dm plus p dv, that is p delta 1 by rho dm. So after substituting all those things, and if I do the manipulation, like taking some quantities into the left side and right side, then what we will get is q dm delta t minus um, this is a delta u delta m equal to delta u dm plus p delta 1 by rho dm, and what we have here is that l m minus lm plus dm delta t, that is dm dt delta t, and we can write this lm minus lm plus dm, yeah, as n by m into dm, because that is nothing but the per unit mass, what amount of composition that is adding over there, which is n into dm, number of particles, some number of particles into dm, that is what is introducing the extra luminosity there because of the dm expansion. So that is per unit mass, which is we are calling as lm minus lm plus dm. So if we write that, then we will get this equation q dm and other than that everything is same as whatever I have written previously. So now So now this is the equation. Let me write it once again. Now if you write in if you do that now if you divide delta the whole equation by delta t, then what you will get as what will you get is q dm minus m by m dm equal to delta u by delta t dm plus p delta 1 by rho delta t dm, which will give us, if I write it as first term, this then this is nothing but the first derivative of u, that is u dot. This is nothing but the variation of 1 by rho, that is 1 by rho dot. Now 1 by rho, here rho is also a variable, which rho is the density, which is a function of m and t, that is function of r and t also, which will vary with the time. That's why it is a variable here. So u dot 1 by rho dot, and other things are there. There is nothing, there is no other time dependence variable here. So these are the main two things. Now let me divide all of the things with dm. Then we will get u dot plus 1 by rho dot, and there is a p, and this is nothing but the this is the l m minus l m plus dm, which can be written as del L del M also, like variation of L luminosity with the mass, because there is changing of mass only, no time dependence. And here we all whatever we are writing is that which is variation with the time, and whatever is variation, what are the variables that is varying with the mass. So our main motto here is to write each and everything in terms of spatial variation and time variation. So we can write this as, so finally what we get is, this is our first stellar no sorry this is the first equation that we got, that we got, and yes, this is the first stellar equation that we have arrived. And this here now you can understand that what it is actually saying. It is actually saying the variation of internal energy and variation of the pressure, variation of internal energy and the variation of the density with the time. That is what is actually creating the difference in energy, which is some amount of energy that is that is generating due to the nuclear reaction, and some amount of energy which is losing or lost due to the luminosity. Because when a star is there, then it is losing energy by emitting the light and giving it to, like, just by radiation. That is what it is given here in this term. And q is the amount of energy that is generating inside a star every per unit mass, and that is what is creating the and this difference is creating the variation of the variation with the time, as well as the variation in the mass, which is going to which is actually propagating over the years, and a star, a primordial star is becoming a giant or a red giant. So this is the stellar equation, which is telling about which is just nothing but the energy conservation. but it is telling us about the dynamics of a star with the variation of the time and just nothing but the variation of the time and the parameters whichever we are using, that is the thermodynamical parameters. So this is the first Taylor equation. But let us go to a condition that as we are considering everything is in thermal equilibrium, that means if it is in thermal equilibrium, then there will be no change in the energy, like Q minus del L del M, that will be equal to 0. That means Q will be del L del M. This condition is supposed to be, this is like case, this is a case 1 or condition. This first equation we have already got, but the thing is, if Q is equal to del L by del M, that means whatever energy of it is producing by nuclear reaction, that amount of energy it is wholly distributed by radiation, then what will happen? Then we will get U dot plus P 1 by rho dot equal to 0. That is equal to Q minus del L del M equal to 0. This is as simple as that. We all can understand. If it is like this, then dl integration, obviously L is a function of M, that's why we can we can write L in terms of derivative of M. So L is a function of M and equal to Q dm, then 0 to L and 0 to M. At this moment we were writing it in terms of partial derivative, but now it is there are no other variables. Like here it was a partial derivative equation, PD equation, because it is a variation of delta T also and delta M also. That's why we need to write in terms of partial thing. But now we can directly write it in terms of D. Here it is as a ODE form, not like a PDE form, just because there are no other variables. Okay, so this is not like special or anything, this is just because of transferring to PD to ODE. So integration 0 to L DLM 0 to M Q dm, then we can write L star is equal to 0 to M Q dm. That is the luminosity of a star. So from the thermal equilibrium condition, we can get for the ideal condition that if the amount of energy whichever is generated inside a star that is wholly radiative, then we will get the luminosity as in terms of QDM, and you can visualize that the luminosity whatever is we are getting, that is nothing but the amount of energy that is generating due to the nuclear reaction inside a star. So now I think this equation is very important, and you can now feel that what the role nuclear energy is playing, and why we are worrying about nuclear astrophysics in stellar evolution and in stellar astrophysics. I hope I am able to make you understand that. I hope this is clear that Q is a energy, that is energy released per unit mass due to the nuclear reaction, and that is what it is giving the luminosity to us. And this equation directly can infer that nuclear reaction is the key which is generating the energy and which is generating the heat, and what for whatever reason we can see a star as luminous object. So that's what the beauty of the stellar equation, first stellar equation, that we can understand. So this is the first stellar equation from what we can get these vibes of nuclear astrophysics once again. Okay, so the total nuclear energy produced by the star in thermal equilibrium, then we can say that the total nuclear energy produced by the star is equal to luminosity of the star. And now we can totally get the vibes of nuclear astrophysics finally by using a model or a star. Like a star is luminous just because of its nuclear nuclear resources. Okay, so this was the first point. Now we'll go to the conservation of energy, conservation of momentum. This is another fundamental conservation law that that we need to consider always. These are the the laws of nature that we need to follow for any system. So if it is so, then then why, how can we introduce the conservation of momentum here? Here momentum is we know that P is equal to momentum is a if we go to the very classical mechanics zone, P equal to mv, and P can be direct, that is a momentum which can be directly inferred with the force, like the due to the momentum which is imparted into a system, that is what is giving us the force, like the difference in the force and whatever is the dynamics of the thing of those things. So equation of the right now, suppose we have a star, like this is a star of mass m, and now dm amount now there is a mass enhancement with the radius enhancement of dm, and that is what it is giving as now it is m plus dm. And here the pressure was p, because there was p, it is p because there was a radius is now changing, and we know that pressure is a function, pressure is also a function of r, like with the change of the volume it will also change. For that reason we can consider that when it was just m mass object, then it has a pressure of r, pressure which is pr. Now if we increase it by, if a star is increased by dr, then now we have pr plus dr. So now and this is obviously now this is the dr thing and r, and this is r plus dr thing. So if we consider a particular part, like let me consider this area, because this is all the three-dimensional thing, I am plotting it in terms of two-dimensional things because we don't have any option. Then this is the area delta H, this is r plus dr, from r to dr it is going, this is a pr and this is pr plus dr. Then what will be the equation of motion of these mass element? And equation of motion means nothing but the, we will equate force, and force means m, here m is delta m, this m, and r double dot, that is a thing that we do, mr double dot, that is a basic equation of a force, F equal to mr double dot. That is what I have written here, that del m r double dot, that is equal to gravitational force plus pressure difference. So these are the two forces, two main reason which is playing a role to make a system stable mechanically, where a gravitational pull inside and pressure force outside is working on it, and they are balancing with each other. And if we can consider that this is a total these are the things which are balancing, but which are the that is the amount of force which are applying to a star, then we can to make an equation of motion, we can consider that this total amount of force that is equivalent to r double dot. Because whatever we do in case of simple classical mechanics things, we consider a system, we find out that what is the potential energy, what is the kinetic energy, that we consider that we equate with the not the, if it is energy then we equivalent with the total energy, and if it is in terms of force then we can write the potential for the force, that is amount of force that is applied for transferring this to this area, or what is the energy that we have lost, for that what amount of force is applied, and we equivalent the force with the mr double dot. We are just doing the simple thing, as simple as that thing here also, for whatever we just do for a classical mechanical thing. So this is a force equivalence things, which will directly infer about the conservation of momentum. If it does so, then let me write it in terms of the variables, like gravitational force, that can be written as g delta m m r r square. Why delta m r square? Because this delta m which is increasing, and beforehand it has m. So what is the extra force that is introducing due to the gravitational things? Because gravitational force is always dependent upon the mass and its mass and the distance between them. So here mass is nothing but the we are considering an isolated system here, so there is nothing like interaction with any external body here. Whatever it is interacting with itself only. So the mass whatever it was there, and the extra mass which is increasing, what amount of energy, what amount of force it is imparting for increasing that amount of mass here. So that is what gravitational force will, that is what amount of gravitational force will include here. So that's why I have written in terms of g delta m as a function of r now, and by r square, and r is the radius. Sorry, r is the like variation which we are considering over the time, over the spatial domain, and obviously over the time also it will vary. And now pressure difference is p r delta s for particular these part we are considering now. Because if you consider for the whole thing, then we can you can like you can like multiply it with the 4 pi r square and all those things, but here we are considering everything in terms of a particular mass element. That's why I have plotted this small piece section of star. Suppose this piece I have taken, and that what I am written here. So that is a delta s, because we don't want to consider the curvature of it. We just want to we can consider a circle with multiple piece of plane here, and we are considering a plane only. That's why we are considering a particular element there, not the whole thing. So that is what that is what I need to mention. And now the pressure difference is nothing but the prds, what delta pr delta s whatever is there, minus pr plus dr into delta s. All right. So if we can if we can write this like, this is the variation again, like whatever we are writing as l m minus l m plus dm equal to del l by del m into dm. Here also we can write it just like the same thing, del p del r. These things can be written as del p del r into delta r delta s. Similarly, like luminosity thing, I have written here, this here. So now the equation becomes r double dot delta m equal to minus g delta m by r square minus delta p delta r delta s. So that can be written as r double dot equal to minus g m r by r square. Delta m I'm writing taking it to this side, the denominator of this of right hand side. Then the delta m will go out, and now whatever we have left with is gmr by r square minus del p del r by del m into del s. This is nothing but 1 by rho m by del m by del r, that is a variation, that is a density 1 by rho, that is a 1 by density. So sorry, del s by del m, these things. Because we are writing in terms of per unit surface area, and if it is dv, that is the total volume, then it is also, we know that del m by del v, that is what is 1 by rho, and here we that is what is rho, and here we are writing in 2D plane. So 2D, for 2D considering a 2D surface, and whatever is there like delta m considering here and delta a is considering here, this is not a 2D also, this is a 3D itself, but we are writing delta m and delta a is format. Then it will be again that 1 by rho, that I hope you can feel that it is nothing but nothing but the density itself. So that, like the amount of mass that is presented over that pillbox. So this is what is that this is what the equation we got. So we know now that dm is equal to 4 pi r square rho r dr, that I have already written previously also. So now if I substitute if you substitute that and write it in terms of like rho dr, then you will get dm by 4 pi r square. So then r double dot is equal to minus gm r square minus del p del m into 4 pi r square. Alright, because 1 by rho dr we are substituting here with this, because we want to write everything in terms of either delta m or either del m or delta t. So now we have this equation. So with the conservation of force, which is in terms of conservation of momentum, then what we get is the second stellar equation, which just give us the like amount of change in the radius, which is just equivalent to we are balancing the force here, force or momentum in momentum in terms of force here. But whatever it is telling us that the gravitational force and the pressure difference are the main thing which is helping us to stable the mechanical to stable the system mechanically. Then from these things we can also understand that what make a star or any celestial object stable, because there is some gravitational pull and pressure difference and they are balancing with each other in a stable equilibrium condition, then only a star can form. So these equations are telling us that first stellar equation, second stellar equation, they are telling that these are the equation in terms of which we can represent a star, and if they follow this kind of situation or this kind of equation, then only a star can form. Last but not the least, hydrostatic equilibrium. Hydrostatic equilibrium. In hydrostatic equilibrium, what will happen? That is what I was telling just right now. If it is stable, if it is in equilibrium, stable equilibrium condition, then what will happen is that this will be the gravitational pull, gravitational attraction, and the pressure outwards, that will balance with each other. That means minus gm by r square, if it is become plus, then it is minus 4 pi r square del p del m, and that means r double dot becomes 0. Like there is no difference in the like there it is absolutely stable. Like whatever amount of, there is no acceleration, there is no amount of extra force which is adding over here, because of the because of this when this kind of hydrostatic equilibrium or the stable equilibrium condition will satisfy, like the gravitational attraction and the pressure outward, they can balance with each other, then only a star will form, otherwise it will not form. So this is the this is what we call the hydrostatic equilibrium condition. And if we can do that, if we can write that, now we have only one variable, so we can write it in terms of ODE form, not a PDE form. So ODE means ordinary differential equation, PD means partial differential equation. So now we don't have any other variable, we just have one variable, so we are writing in terms of ODE now. So that is equal to dpdm equal to minus gm by 4 pi r to the power 4, and obviously m greater than 0, r greater than 0, that is no need to tell, it is obvious. Then if m equal to 0, greater than equal to 0, and r greater than equal to 0, that means dp dm is always less than 0. That means a important consequence is there. Mass increases with r, which in turns, what it provides to us is that pressure decreases with r, like the as it is increasing. Okay. So this is the hydrostatic equilibrium condition, and we can further go with these and study in terms of like the pressure in the core and total internal energy and the gravitational potential, and we can write it in terms of gravitational potential energy, and then we will reach to some other the ideal gas equation, what we get obviously if it is in a stable equilibrium condition and it can behave like that manner, then we can consider it as a ideal gas kind of things, which are the composition there in the star. And that is what is another consequence which will give it to us, is that why we consider Maxwell Boltzmann distribution inside a star thing also. So that is why I wanted to discuss about the stellar modeling of a star, because it can give you the feel with the first stellar equation. You can understand that the total amount, the energy whichever is there due to the nuclear reaction, that is what it is providing us as a luminous object, as a star. And second thing is that second thing this second stellar equation, which is telling that how why a star will form and how a star will form. There are many conditions, like there are many in interstellar medium and in intergalactic medium. There are lots of amount of hydrogen is there, but everything every time does not form a star. When a stable equilibrium condition will reach between the gravitational attraction and the pressure outward pressure force, then only it will form a spherical object like star. And that is what it is telling in terms of second stellar equation. And third stellar equation is not nothing just but the condition that is we are applying, and which gives us a great consequence that mass increases with r and pressure will decrease with r. And that's how the gravitation starts to win. And that at that moment when gravitation actually wins over the pressure, then it will explode to supernova. So by these three equation, like first equation, you get that why a star is luminous, because of the nuclear energy, that because of the nuclear reaction it is happening there. So you can get the idea of nuclear astrophysics here in a broad spectrum, why you want to do this. And next thing is that the conservation of momentum with the using which we can get the second standard equation, which is very beautifully telling us the condition of stability, that when a star will form and when a star will not form from the interstellar medium or intergalactic medium. And when we reach to the hydrostatic equilibrium, then we can get the idea that with the mass increase, r is increasing, pressure is decreasing. That means after a certain time the gravitation will win over the pressure and it will collapse into the supernova. That means with these.
Ma'am,
Yes.
ma'am, if gravitational energy wins, then it will become a white dwarf. If the
So
pressure,
yes, yes.
if if the pressure increases, then only it can become a supernova. That from inside the pressure is getting very high, so there will be an explosion. And if gravitational energy is greater, then it will contract into a white dwarf.
Yes, but yes, you are right in that way, because this is where the role of mass came into play. Okay. So if you want to go into that details, like when supernova will happen and when white dwarf will happen, but you catch the thing very well, because this is what the role of mass come into the play. And when I am not showing you, this is a very ideal model of the of doing a modeling of a star, and this is a very simplistic model of doing the modeling of a star. So I just wanted to give you the broad view, that in that respect I am telling about this. But yes, if you consider the mass variation also, then you will be able to see with the equation, if we go further with the energy, then when the mass is about 10 solar mass, then it will explode into the supernova, and if it is lesser than that, then it will be contracted within a white dwarf thing and produce some planetary nebula. So but I will not go into that much details here. Okay.
Okay, ma'am.
Yes. So so yes, but yeah, the point is absolutely correct that here two things are we need to remember, that is mass and pressure. So both are playing some role, and mass means the gravitation is coming into the role, and coming into the play to play some role there into it. And if you get that if you go further, that like there are some more equations there. I am writing whatever equations I have written, and that I am doing just directly at this moment, because if I do this, then it has more 10 or 10 pages more to do some sort of things. I'll not go, I don't want to go to that much details. So yes, so the things you need to remember is that mass, pressure, radius, time, everything is playing a role in terms of stability and instability. When the pressure both are stable, when it is a stable system and gravitational pressure are equivalent, then it will be a stable star. And with the variation of the time, with the first stellar equation and second stellar equation, first stellar equation, we can see that it will increase with the mass, and whatever the extra amount of reaction is getting, that is getting we are getting as a luminosity. And the end stage of star will be either white dwarf, or for a main sequence star, mostly it is white dwarf. And if it is a red supergiant that is greater than 10 solar mass, then it will be a supernova. And there will be type 1a supernova, type 2a supernova, there are many things there. So the main thing that is a take home message from these, that with the modeling of a star we can understand the from a general formation of a star to death of a star. That is what is the main goal, and that is what is the main goal to study any system, that we can know about its dynamics. And that is what it tells from these three equations only. So yes, this was the thing. And there are more things, but I will not go into that. Rather, I will start solving few more questions. Not few more questions, I will start solving the questions. I had a plan to discuss the week 6 questions also, but many you have already responded that week 6 questions of assignments were pretty easy, and you were able to calculate all the spin parities whichever I was discussing for the previous 2 or 3 lectures, and you did not find any problem in that case. So I will probably not discuss about the assignment 6 question that I think that is I am deciding at this moment, because there is no point of wasting time, as you have already uh, done that, and you also know how to solve that because you have done that. Okay, so I'll go with some basic questions and some revision questions which I have made, and this will help to revise you the whole the things that you have learned. And I found out that there were no question related to the luminosity or the distance, astronomical distances in the assignments. So I have few questions which that I will discuss now. Okay. So and in this case I have not written the questions in any slides, so I'll write the questions here itself. So please write the questions, or visit the drive after completing this class to see the questions, or you can visit the YouTube link also. I hope by now everyone is aware about the YouTube also, that you can go there to check the video lectures, as well as to revise anything. If you find that you need to revise, then you can visit the YouTube channel also. Okay, so let me start with the questions. So the question was is telling Betelgeuse has a diameter Who had heard about Betelgeuse? This is not, none of this course perspective. I'm just asking that whoever is amateur astronomer here who has seen Betelgeuse.
Ma'am, I found.
You saw where
Yeah,
it appears?
I found. Ma'am, I guess in Orion constellation there is a four stars. In one star, it's like a yellowish color, ma'am. We tell this,
Okay, all right.
right?
Everybody, anybody is here is amateur astronomer, and you
The
have
part of the Orion constellation,
okay.
and it is a red supergiant.
Yes. Yes. So if anyone have any telescopic telescope thing that you can see with, even if you have a maybe no, or maybe yes, or whatever. If you have any telescope facility or where you can visit, then you can do these kind of things to enjoy the night sky watching things. I had a pretty good image of Milky Way arm. Suddenly, I remember. If I found that, then I will show you next time.
Okay, ma'am.
All right. So Betelgeuse has a suppose the question is Betelgeuse has a diameter of about 1800 solar radius and a distance of d 220 parsec. What is its angular diameter in millisecond? Very basic questions, milliard second. But these are the very basic questions that I have put there for today. But I want that you guys also please try these things. I think you guys should be able to do these things because whatever I am giving it as a question today, that those topics I have mostly discussed with you. So I'll give some minutes. If anybody has any idea, then please let me know how to calculate, or maybe please tell the answer. I think now you can understand what you need to do. Anybody? Nobody? Okay, so it is telling that Betelgeuse has a diameter of about 108, 1800 solar radii and a distance of d is equal to 220 parsec. What is its angular diameter in milli-arc second? So angular diameter it is talking about. So distance is mostly we consider this distance, but as it is a far distant object, so we can consider it this thing as d also. We don't need to bother about root over of d square and r square, all those things we did not, don't need to consider these because of in case of in case of astronomical distant objects. For that reason, if we consider, and here also it is talking about the angular diameter, not the radial. So angular diameter means you don't need to consider the half of the diameter and all those things. This is a very simple question, and it is just talking about the angular diameter. That means you need to just calculate this by this. Now conversion that and this will be in radian, and the conversion if you do, then it will be approx 9 astronomical unit by 220 per sec. I have already done this by myself, so that's why I can write it so smoothly. You can obviously calculate how to find out in astronomical unit, in parsec, and all those, because I need to transfer it into the parsec also. If we do that, then what we'll get is 0.074 arc second, and that is equivalent to 74 milli arc second. So this is the angular diameter of the angular. This is the angular diameter of the Betelgeuse.
Ma'am,
Yes.
ma'am, I am asking a different question, not related to this course.
Yes.
Actually, 100% different.
Hmm.
Ma'am, actually, which pad you are using for writing? For
Okay.
writing.
For writing purpose, I am using iPad.
Okay.
There is a one software, one thing that is called Good Notes. So I am using Good Notes in iPad.
Okay. iPad.
Hmm.
Okay. Then okay. Tab.
Yes, Apple iPad.
Apple iPad. Okay. Okay. Okay.
Yes.
Thank you.
So this is a that was a question one, and now it is all right now. If I am using this, like there is no problem in my handwriting or understanding the written whatever I am writing, all those things.
No, no, ma'am. It is basically very good. That's why I am asking.
Okay.
Uh, what which gadget you are using?
Okay, okay. All right. If anybody has anybody found anything, then you can also tell me that if my handwriting is not going well and all those things, you can also tell those things, because uh, that happens. That if you cannot understand something, then also I need to know. But okay, all right. So yeah, next question. Next question is two stars have apparent magnitude of m1 equal to 1 and m2 equal to plus 6, then what is the ratio of their fluxes? Let me write the question because I don't have the questions this time with the slides also. And I talked about apparent magnitude, absolute magnitude, volumetric magnitude, and how to calculate those, what are the formulas, all I have discussed in very detailed manner when I was going for HR diagram. And I think, and I have discussed all those things, and I found that there were no question related to that in an assignment. That's why I am giving you some questions here today. But everybody has remembered all those things. Do everybody remember those things that I have discussed? I think okay, all right. Maybe people have forgotten because it is very natural to forget. I also used to forget, but yeah. Even if you forget, then please go to those lectures notes and the lectures. Maybe it was week 2, week 3. I forgot. Then you will find out again that what was the apparent magnitude definition of it. what is there is what is the volumetric, what was the absolute magnitude, all those things. But today I will again discuss those things by doing these problems, by solving these problems. Maybe you will remember, maybe you will start to remember all those things, that whatever what was there. But please visit to the drive folder. There all the things are there. And there is one more thing, that on the regular basis, or mostly in the weekly basis, I used to upload few other documents also, which I found interesting. So go to those things also if you are finding it interesting, and I find those things interesting, that's why I put it there. Like there are some neutron scattering sigma v things, that formula sheet, one formula sheet kind of things are there, that's why I have put there. Maybe you can check that. Today or yesterday, maybe I have put one paper there, which is about a nucleosynthesis. Yes, that is a S process, R process, P process. The paper of Mayer that was talked about in the classes also. That the original paper that I have also put there. So those things you can go through, and you can check those things also. All right. So yes, so please, revision is very important in any course. So keep visit all these things, and you can visit the YouTube videos also, whatever. So the question 2 is telling two stars have apparent magnitude of m1 is equal to plus 1 and m2 equal to plus 6, and what is the ratio of their fluxes. So I will not discuss that what is the apparent magnitude, absolute magnitude, or volumetric magnitude at this moment, because I have discussed about those definitions and formulas elaboratively. I will directly write the formula now. The relation between magnitudes for apparent magnitude and the flux density is directly we can write it in.
Scaling factor and log F, log of the flux.
Yes, m is equal to some c plus 2.5 log
Scaling
of flux.
factor.
Yes, this was the thing, right? Hmm?
Yes, ma'am.
All right, so this was the formula. Now if I have two things, m1, m2, and these constants, this scaling factor are same, so I don't bother about those things. I will not bother about those things. So if I can write it in terms of these, then this is log 10. So this is nothing but now we want to find out f1 by f2. So it will be 10 to the power m1 m2 minus m1. Mm, I wanted to calculate f1 by f2, and maybe f2 by f1. Written something or here something. So 6 minus 1, that is 6 minus 1 by 2.5. There is a 2.5 factor there. So 10 to the power 5 by 2.5. Then 10 square, that is equal to 100. So if you find the ratio, if you get the ratio, then you will get the ratio is as 100. So the main formula is as like I think Gothuli has mentioned, or somebody has mentioned, that this was the main formula. From that we get this, and when we get this, then we and this is the question that was given to us, that what will be the ratio of the fluxes. So please go to the class notes again, and revisit that what was the apparent magnitude, absolute magnitude, volumetric magnitude, relation between these things with the fluxes, and the luminosity with the distance, and all those things. I have given this problem just to just for the revision purpose only. So the question 3 is saying the star Alpha Centauri A has a luminosity L equal to 1.5 L star L sun. Its absolute magnitude M, capital M, and apparent magnitude is small m. Sorry, L is equal to 1.5, and I forgot to write the informations. L equal to 1, I am extremely sorry. L equal to 1.5 L sun, and lies at a distance of 4.37 light year. Actually, I just made this question today morning, so that's why I was unable to write those things in slide, and it took a lot of time for me to do these things. So that's why I am writing the questions also. So these are 4.37 light years. Then what are its absolute magnitude m and apparent magnitude small m, and what then is its distance modulus? So this is the question. The star Alpha Centauri A has a luminosity L is equal to 1.5 solar luminosity, and lies at a distance of 4.37 light year. What are its absolute magnitude m and apparent magnitude small m? And if it is so, then what then is its distance modulus? So first thing is that capital M, which is the absolute magnitude, that is equal to, the formula is 4.8 minus 2.5 log of L by L sun. That is the formula with which you can directly calculate it. With which you can directly calculate the absolute magnitude. Then it is 4.8. Like I can write this in terms of L sun directly, because in case of absolute magnitude, I told you guys that absolute magnitude is always measured as in terms of, if it's whatever distance the star is there, that is there, but we calculate it if the star was at 10 parsec distance, then what will be its magnitude? So this is the ratio of that, and that's why you can if then what will be the magnitude? That is what we call the absolute magnitude. And in case of that, we can compare it with the solar mass, and if we write that in terms of solar magnitude, then we can do the ratio and the 4 pi things that cut out, and what we get finally as the formula is 4.8 minus 2.5 log by L sun, that you can deduce by yourself, or you can just directly remember by yourself that it will be what is the formula in terms of solar thing. So if you get that, then then you can substitute these, and that it is told that L is equal to 1.5 L sun, then it will be 1.5, then it will be 4.8 minus 0.440, that is equal to 4.36. So we have calculated the absolute magnitude. Now we need to calculate the apparent magnitude, that is equal to small m, and that will be nothing but capital M plus 5 log d by 10 parsec. How? Because we know that m minus m is equal to minus 2.5 log of d square by something d square by 10 parsec square. This kind of thing was there. If 2 is coming, then it is 2.5 into 2, that is 5. Then m, that is we need to calculate the small m. We know the capital M, then we have to substitute this thing there and this thing there, then we will get this formula. Then if we do that, then what we'll do is d equal to 4.36 from this plus log of 4.37 by 3.262 into 10. Why I am writing this? Because it is given in the question that at a distance of 4.37 light year, that means d is equal to 4.37 light year. And if you want to convert it in terms of parsec directly, then just divide any length light year, that is with the 3.262, then what you will get is the in terms of this parsec. And now if you calculate this, that is, now it is numerator is also in parsec, denominator is also in parsec, then you can directly divide it and calculate the apparent magnitude, and that will be 4.36, and it will this is a plus, and it will come as minus of 0.873. If you calculate, then it will be 3.48. That is the apparent magnitude. Now we have to calculate absolute magnitude, apparent magnitude. Both of them are already calculated. Now you have to calculate the distance modulus. What is called the distance modulus? Distance modulus is nothing but the m minus capital M. That is what we call the distance modulus. Then it is 3.48 minus 4.36 equal to minus 0.88. That is what is the distance modulus. So this was the second question. This was the third question. So now the question 4. Question 4 is telling two stars have the same luminosity but star B is 10 times as far as star A. Give the ratio of their fluxes and the difference in the apparent magnitude. Ratio. So you need to calculate the ratio of their fluxes, and this is the first thing, and second thing is the differences in the apparent magnitude. So difference in term and luminosity and distance is what is given to you. So we know the FB by FA, which we need to calculate, is equal to LB by LA by dB by dA. Why is that? Because we know the relation between flux and luminosity. We know that luminosity by the distance square, that is what the flux is proportional with, 4 pi d square. It is F is equal to L by 4 pi d square. So two variables are luminosity and the distance. Then FB is equal to we can read FB by FA, that can be written as LB by dB square by LA by dA square, and the 4 pi things are gone. Then what is left with LB by LM by dB by dA square. That is what is written here. Then if we do so, then what we will get, FB by FA is equal to 1 by 10 square is equal to 10 to the power minus 2. And if you talk about the difference in the magnitude, then MB minus MA is equal to 2.5 log FA by FB, that is equal to 5. Why it is so? Because M is equal to some constant C plus 2.5 log minus 2, like it is like this, M is equal to 2.5 minus 2.5 log some F plus some C. So if you do the MB minus MA thing, then the CC cut out, and minus of 2.5 of log of F, that means 2.5 log of 1 by F. Then what you will get is M for MB, the FB will be in denominator. For MA, it will be in the numerator, then finally what you will get is as 2.5 log fa by fb, and that is equal to 10 square log of 10 square, that is nothing but the sorry 2.5 into log of 10 square, that is nothing but the 2.5 into 2, that is how you get 5. So you need to modify the equations, like you need to play with the equations. The main now, like at the beginning someone was asking about I am to solve the questions and not understanding what is the main equation that is need to be used here. So for that purpose I can say that you just need to remember this thing: what is apparent magnitude from its definition, what is absolute magnitude from its definition. If you know that, then you can easily calculate, then you can just manipulate these things, that what is given to you, what you need to find out, and how you can play with the flux density, luminosity, all those things. If you can do these things, then you can certainly manipulate the equations and find out that what is actually given to the question to or ask, what is actually asked to you to for the question, like to solve the question. So from these thing I think you can understand that how to solve, like you don't need to remember everything. That is what you, the problem you are facing, you are telling to me that how many formulas you need to remember. You don't need to remember everything, you just remember the definition part mainly, that by definition what is apparent magnitude, by definition what is absolute magnitude, that's all. And how flux density and absolute magnitude, how the flux density and the luminosity is connected with each other. If you know that, then you can do any kind of this kind of question. These three formulas just you need to remember. So this was the question 4. Now question 5. It is very easy question, and I would like to hear from you that how you will you do this, because this is just very basic question. Like, assuming Earth has an average temperature of 50 degree Fahrenheit, or maybe I can tell you like you need to calculate in Kelvin. That is one part of this question, or maybe I can give you directly the Kelvin value also, like suppose it is 300 Kelvin. Then compute the peak wavelength of Earth's blackbody radiation. What part of the EM spectrum does this line? So you need to tell this thing, that how will you solve it. Anybody, please, how will you solve it?
Ma'am, like that E equal to HC by lambda, and in E we can place KT. Means KT equal to HC by lambda. From that relation we can find out the lambda.
Okay, that's possible, but hc by lambda equal to, you are telling equal to kt, but I am not telling you about it is thermal radiation, or okay, I am not talking about thermal radiation though. So can you use this? I am talking about black body radiation. Think when we can use that equal to kt.
for the most probable energy,
Most probable energy.
and all kinds of energy in the nuclear astrophysics we can use equal to KT.
No, but that is average energy in case of any system which is doing thermal radiation in thermal equilibrium. Like we that like thermal energy is another energy. Like, uh, do you think that a blackbody radiation card and a Maxwell Boltzmann radiation card are same?
No,
No, no.
no.
So when we talk about the thermal radiation, like thermal energy, then we use the Maxwell Boltzmann thing.
So,
And
then, ma'am, we can use that equal to sigma t to the power 4, that Stephen Boltzmann thing for black body radiation.
okay, now you are getting the point that we need to think about the black body radiation here. The main thing which you need to think is black body radiation. ठीक है? ठीक है? So now if it is black body radiation, then you have the formula equal to sigma t to the power 4. That is all right. Now, do you have anything else? Sigma t to the power 4, sigma, if you know that 2.4 into 10 was something, then you know that. But
Yes,
here
ma'am.
it is talked about that you need to calculate the black body radiation, the peak wavelength of Earth's black body radiation, peak wavelength, and you have some formula which direct talk about lambda max.
Yes, ma'am. The Planck's law of radiation.
Which
From
is the
gamma peak.
yes, yes, tell.
Ma'am,
Planck's Planck's law of radiation can be used like 2h square by lambda to the power 5.
Hmm,
Mean for
something
black
some
body radiation.
it is as it is black body radiation, and you know something called Stephan's law, Stefan,
Yes, ma'am.
and all those things. Can you find out something that which directly relate lambda and t? Anybody else? Somebody? Anybody? Whoever is talking, please. So this is already discarded now. That KT cannot, we cannot do that. That is clear, na? That you have only understand, that you have only told to me. And by this way you need to think that if you are thinking about KT, is that possible? What is the information given to this problem? What is the information given to it, given for this problem that we need to do? If it is black body radiation, so we cannot do the Maxwell Boltzmann thing and the thermal radiation thing, so we can't do that. So what we can do is we need to something think about black body radiation. And black body radiation, we know about this relation that lambda max t is equal to constant. We know that we know this now.
Yes, ma'am.
yes, ma'am.
Yes. So if we know these, then we there is like it is talked about like for Earth it is given. So we need to calculate the peak for the Earth radiation. Earth at a black body. If Earth is a black body, but you will tell that how I'll remove this constant. Either you need to know this constant, what is the value of the constant, that is well given in the books. But if you suppose don't remember, if you don't remember that what is the constant, then you must have this idea, like these are the key factors that I am just trying to give you the notion that how to solve the problems, because you guys are facing problem in solving the problems that you told when the class started today. That's why I am elaborating in this way. Like you feel that at 6000 Kelvin there is the 500 nanometer radiation. We always get this 500 nanometer radiation, about 500 nanometer radiation in 6000 Kelvin. Okay, so if this is a standard thing that we always use, if we can always if we use this thing, then we can compare this like lambda max. We need to calculate it for this Earth by lambda max standard, STD, then 1 by T Earth, 1 by T standard. If you have anything like this kind of standard thing, you need to consider, like, luminosity of sun, luminosity of radius of sun. These are the standard things in 1 AU, 1 light year, all those things. That and in this case, the radiation of 500 nanometer wavelength is at 6,000 Kelvin. That is also a standard thing that we consider. Like the 300 Kelvin, we always consider the room temperature as 300 Kelvin for for any experimental perspective or anything. So these are few values which you need to get into your mind, that if I don't have anything and I don't remember the constant, then what will I do? I'll direct compare, because ratio is a very important thing with which you can calculate many things. So if you know that, then you can find out the lambda max of Earth and T standard. That is, maybe I have not given the I have not given you the 1 minute. I haven't given you this information regarding this 6,000 Kelvin and 500 nanometer, and this was also in this question. Mostly this kind of information will also be given into the question, but just to give you a feel that if you don't have, then you need to remember some standard values. For that reason, I have not given this information into the question. But remember, you will get this kind of question, this kind of information in questions also mostly. So if you have that kind of situation, then you can directly take the standard values and calculate it. And if you calculate, then it will be 500 into 6,000 by 300. Then what you will get is 10,000 nanometer, which is about 10 micrometer. Now you have to tell me that in which, if you consider a spectrum, EM spectrum, whole range of spectrum, then in which range this 10 micrometer will fall. Like it is visible, if it is radio, it is infrared, this is gamma, this is which is this 10 micrometer. Because by the end of this course, I want that you guys have a pretty good notion of the whole EM spectrum. That is very important, because you will realize by the time when you will have this feel that getting know the whole EM spectrum is how much important. Because we can see the visible part only, but there is whole lot of amount of information is hidden there in other part of the EM spectrum. And that's why we have radio telescopes, we have gamma ray telescopes, we have IR telescopes, we have many other X-ray telescopes, many other telescopes are present there, just to get the whole idea that that is hidden over these other EM spectrum. So let me know that which electromagnetic
This
radiation
is
it is talking about.
infrared.
Yes, this is infrared. Absolutely correct. Okay, all right. So I have six, seven, eight, a few more questions, but time is already over. Let me know that if you want to do these problems today, or I'll carry forward these other questions in the next class. I don't like whatever you want, because if it is like already 2 hours, then you can also tell that no. But if you are all right with this, then it's also fine.
Yes, ma'am, we can do it.
Okay,
Yes, ma'am. I will proceed now.
okay. So the question six is telling a red giant star has a temperature of 3,000 Kelvin. And luminosity L is equal to 1,000 L sun. About what is its radius? R in R full. So it is given that a red giant star has a temperature of 3,000 Kelvin, fast information, and luminosity is also given, that is 1,000 L sun. What is the radius of this red giant star in terms of solar radius, obviously. So, do you remember any formula or any relation, any proportionality that how the luminosity, temperature, and radius varies?
Yes, ma'am, that L equal to 4 pi sigma r square and t to the power 4.
Absolutely correct. Very nice, very nice. So, if we do that, L is equal to 4 pi r square t to the power 4. If it is like this, then we can compare it with L solar, L sun, that is r sun square, t sun square, 3 suns to the power 4 by r. Sorry. R square t to the power 4, r sun square t to the power 4, then it is r by r sun whole square, t by t sun whole to the power 4. Then what we'll get? Then what we'll get is this. Now we have the information of luminosity, we have the information of temperature. What we need to calculate is radius. So r sun is equal to L by L sun whole to the power half, t by t sun whole to the power minus 2. So that is equal to 1000 whole to the power half whole to the power 2. What is why half to the power 2? Because t is talked about, like t is given as 3000 Kelvin. So that means 6000 Kelvin by 2. If it is 6000 Kelvin by 2, 6000 Kelvin is the solar temperature of the surface. So T sun by 2. So T by T sun is equal to 1 by 2. So T by T sun. So T by T sun is equal to 1 by 2. So we minus 2. So you have everything now. You can calculate R by R sun. Just you need to solve this. Now the question 7. Question 7 is telling that a line in the hydrogen spectrum has a wavelength of 4.34 into 10 to the power minus 7 meter. A line in the hydrogen spectrum has a wavelength of 4.34 into 10 to the power minus 7 meter. When detected on Earth from a distant galaxy, the same line has a wavelength of 4.76 into 10 to the power minus 7 meter. What is the speed of the galaxy? Recession velocity, actually. Like with which speed it is going as the universe is expanding. So this problem, exactly same kind of problem, was done in the very first discussion, I think. And there is a standard formula, standard thing, Doppler shifting things that you can use and solve this problem. Can you guys do this, or I need to solve this? Like the lambda 0 is given, if it is shifted, then what is the lambda that is also given? Yes,
We have to subtract the lambdas and find the redshift.
we have to subtract a lambda, then we got the delta lambda. That means first we need to
Yes.
calculate delta lambda, right?
Hmm.
Then
Delta lambda and then divide by the lambda.
That is a lambda
Then
0.
we will get that V by C.
Then we will equate it with the V by C.
We-
Right?
Hmm.
Then we will get V is equal to delta lambda by lambda 0 into C. That is equal to, if you calculate, then it will come 10 to 2.90 meter per second. You can calculate it by yourself in your home. Now the next question is a bit interesting, and with which you are not introduced yet in a very good manner, because that is talked about cosmic scale factor. Do you know about the cosmic scale factor? I don't think that I have not discussed about that, and in the lectures also it was not there, right?
No.
Okay, so there is something called cosmic scale factor that I introduced that in a question, and I wanted to calculate that, and as well as I wanted to tell about the cosmic scale factor in very brief manner, so that you can solve the question and you can understand what it is. But maybe I can start with this from the next class, like what is cosmic scale factor, and I will solve this question and further move to the week 7 discussion, because it is already at the end, and introducing a new concept at the end is not very good, I think. So let us stop the discussion here, and there is only one question that is regarding that cosmic scale factor. From that I will start from the next class. All right.
Okay.
Okay,
Okay,
so
ma'am. Ma'am, and find out your galaxy wing picture, ma'am.
what?
The galaxy wing.
And that Milky
So
Way
you
photo that you said
told
you will
me,
share.
right?
Okay, okay, in that in website.
No, ma'am. You told me, right, ma'am. You took the picture of that galaxy wing or.
Yes, yes, yes.
You took the photo of that Betelgeuse in the
No, not
Orion
Betelgeuse, that
constellation.
Milky Way galaxy. Yes, but right
Means,
now I don't
galaxy
have
wing.
at this moment with me. I will maybe find out and show it to
Ah,
you.
okay, ma'am. Okay, ma'am.
Okay,
Okay.
And
I
also
hope.
the binding energy, that sum also, ma'am.
Oh, binding energy thing that
Efficient
I
system.
actually forgot.
Ah,
Binding
yes.
energy thing that what exactly I told to you to calculate for the helium.
Ah, yes, ma'am. Helium, ma'am. You told me.
Okay, so probably I remember. Okay, nice. So for the helium thing, maybe I'll do it and upload in the drive, or maybe you can do it and send it to me in the mail. Or I think I have also done it in one of the discussion session. So please find it out in the drive folder, and I think I have done it, and that's why I told you to calculate it again. But if you not if you are unable to do it, then I'll please contact me with the mail. I will definitely contact with you with the mail. Okay.
Okay, ma'am. I will go through the PDF. If I have any doubt, ma'am, I will ask through
Okay,
mail,
okay,
ma'am. Okay, ma'am.
okay.
Okay, ma'am. Thank you
Very
so
nice.
much, ma'am.
Okay, bye.
Bye, ma'am.
Bye.